So yeah, this is basically our last lecture. Thursday is your final exam. It'll be the full 2 hours, and I'll have 2 hours of lab hours after that. But there's no labs left. So this will basically be it. Um, and my plan today is to talk a little bit about Lab 5, Homework 6, Homework 7, sort of wrap up all the stuff that's been turned in, see if there's any final questions on Lab 6, talk a little bit about the exam, and then just kind of spend the rest of the class period going through all the other stuff that we could talk about in this course if we had a lot more time. There's actually like 4 chapters in the book that we don't get to, which is talking about performance, memory and storage, concurrency, and networking. These are all topics that are worthy of an entire class in themselves, but we touch on them a little bit in here because this is basically an architecture class plus some other stuff. So we'll fill our 2 hours today pretty easily. So let me start with Lab 5. So Lab 5 was the timing lab where you did pulse width modulation generation, and that worked really well for most people. So and the write-ups that I got in the lab were fantastic. So that was really good. So people put waveforms in there, and you could see the duty cycle modulating, and it was generally modulating at a half-second interval from one duty cycle to another. That was all great. There are some people who weren't able to get a waveform to generate, and my general comments were twofold. One, the obvious: come by lab hours if you want to work on the code. Screen share, show me what you're doing, and we can work on debugging it together. But the more general comment is more complex programs like this, a good way to develop them is to build them up in pieces, right? So there were a lot of pieces to Lab 5. It was getting the timers to work and the interrupts, right? And then being able to change the interval for the high part versus the low part of your waveform. And some people did that by modifying the timer register. Some people did it by counting. But being able to generate a non-uniform duty cycle, and that's a significant leap beyond a plain old square wave. And then doing kind of the state machine part of every half second, changing the state of the system so that if you were doing a 75% duty cycle, now you do a 50%. So doing that, and then adding the extra half second blink on the other output pin. It's a lot of pieces, right? And my suggestion is start small. Well, smaller, right? It's not small. It's a huge piece, but just make a waveform using the timer, and maybe try 2 different ways to do that. Maybe just do it by setting the timer variables, and then try to do it with this 1 millisecond timer, but by counting. So count up, to 250, toggle the output, count to 250, toggle the output, and just keep layering it up from there. So if you want to work on that, right, come by lab hours, and we can run through the debugger on your code and see how far it got, and get some practice on debugging code in general. The other comment on labs that I wanted to make, just for future reference, right? There's this thing called the 5-word rule. It goes by different names. Sometimes it's the 6-word rule and so on. But it's this kind of rule of thumb for plagiarism in written reports. And the strictest standard is the 5-word rule, which basically says if you have 5 words in a row that can be found somewhere else, that can be considered plagiarism. And that's it's an approximate rule, because sometimes you've got to use the same 5 words. There's no other way to do it, right? So set tri-state A to 0, right? Well, if you put that in your lab and somebody else puts that in their lab, that's not plagiarism, right? Because you're setting tri-state A to 0, right? But I mention this because a number of people are taking paragraphs from the lab assignment and pasting that into the beginning of their report. So they have a paragraph talking about pulse width modulation, and it's word for word from the description that Izad wrote, right? Technically, that could be called plagiarism. And the way you avoid that is just put a notation at the bottom of anything that you copy and paste and just cite it. Say where this came from, right? And some people are doing this. They say, taken from ENGR270 / such and such. Or taken from Lab 5 write-up, Engineering270. But something in there just to make it really clear that you're not claiming that you wrote these words, right? And it's not a problem in here. I'm not worried about it. But going forward, at a university or, on a job or things like that, it gets, increasingly scrutinized. So just get in the habit, if you ever copy, words or pictures from anywhere else and put it in a report, and that report has your name on it, always list a reference for where that material came from, so that somebody doesn't accuse you of, claiming that you wrote this or you drew this picture and so on. So that's just kind of a going forward thing to keep in mind. All right, homework 6. I mainly looked at the first batch of questions related to timing. So questions 71 through 79, which was kind of the prototype for all the rest of the timing questions. But it was, the standard 32K system clock, 8K instruction clock, and then kind of building up the logic for, how long does an instruction take, which is 1/8 of a second to do 1,000 instructions. And then answering some questions about, different values in the initial timer registers and how long the timing interval is for those. There was a typo in all of that, unfortunately. And a few people noticed it and did this the way it was written. So 32 kilohertz system clock / 8,000 kilohertz instruction clock. So those don't go together. A 32 kilohertz system clock would be an 8,000 hertz or an 8 kilohertz instruction clock. 8,000 kilohertz is actually 8 megahertz. And 32K system clock, 8 meg instruction clock doesn't make sense. So that's actually a typo, so that should just be 8,000 hertz. But some people went ahead and used an 8 megahertz instruction clock and then got the correct numbers from that, so that's fine. But if you were confused about that, that was just my bad. I just typoed that. And I fixed it now, so next summer, All right. So the most important part of today is probably homework 7 questions. And homework 7 was these questions about indirect file register access. And I'll get these graded sometime tomorrow, and I'll probably get these posted, by the end of Wednesday. But, you'll probably see a question on your exam on Thursday related to indirect file reference. And so if you have any questions about how this stuff is working, I want to talk about it right now. And I want to make sure that everybody feels like they can do these questions absolutely perfectly, no question about it. And as with most of these coding questions on homeworks, you can run this code in MPLab and see if it works or not. But if there's any questions about any of this, let's talk about it right now, or come by lab hours, right, or both. But if there's no questions, I'll probably just pick a few of these and go through them. But let's start with, specific issues that people ran into. And I haven't even looked to see how many people turned it in yet.
I felt like most of it was pretty straightforward.
Okay. That's encouraging. So what does this code do? This program for 137? Actually, I don't remember. So what goes on in this code?
I remember that it was going to increment infinitely. So if you move hex 40 into the main register, and then you move that to the lower indirect register, FSR 0, and then you move 7 into the register, you increment the indirect register plus 7, hex 7.
Okay, so what addresses that the first time through?
That would be hex 47, and then you add the literal to 47 FF, which is 255, and you're just going to keep coming back to hex 47 and incrementing it again and again and again forever.
So we add FF to W. What does that make the value of W? So if W equals 7, and then we add FF, what's the new value of W? Someone already said it in chat. So what is FF? If we write that in binary, what does that look like?
Well, it's just all ones.
It's a bunch of ones. So is that a positive or negative number if we think 2's complement? Do you remember the trick for telling the sign of a 2's complement number?
You flip all the bits and add 1.
Well, that tells you what the negative value is, but to just look at an 8-bit number written in 2's complement and know is this positive or negative, you look at this most significant bit. And if it's 1, it's negative. If it's 0, it's not negative. It's either positive or 0. So this is a negative number. And so if we do that trick of complement the bits and add 1, we'll get the positive value of this number. So if you take 1, 1, 1, 1, and you toggle all the bits, you get a bunch of zeros. If you add 1, you get just good old 1. So this must be the negative of that. So 0xFF is actually negative 1 if we take this as a 2's complement number. So adding FF to W is the same as subtracting 1 from it. So this business over here of add LW 0xFF, that really just subtracts 1 from W.
Oh, I thought it did mask it.
Oh, so it's an add, not an and.
Mm-hmm.
Yeah, typo. But you're perfectly right if that was just an N. All right, so yeah.
Through my head that thought it was hex 47 that was being incremented again and again, but I guess it was just a move literal.
Okay. All right, so yeah, we subtract 1 from W. If it's not 0, we go back here. So W will be 6. We'll increment the file select register's value, which is still 40, plus W, which is 6. That'll say increment file register 46. So it'll do 46. And it'll certainly do 41. And then when we add minus 1 to W, W will become 0. It says branch if not 0. Well, 0 is 0, so it will not branch. So this will actually clear file registers 47 through 41. But it'll stop at 41. It won't go on to 40. And so it'll just fall through to whatever. Any worries with 138? We kind of did this one last week. Different locations in memory, but moving a block of stuff.
Could we go over this one?
Yeah. MoveFF will work perfectly fine. And that's a really intense instruction, MoveFF postinc 1, postinc 2. So what do we want to do here? Use indirect addressing. We want to copy 16 bytes from 40 to 80. So easy way to load file select register 0L and 0H is to use this load file select register instruction. This says I'm doing FSR 0, and this specifies a 12-bit number, and the low 8 bits will get loaded into FSR 0L, and the upper 4 bits will get loaded into FSR 0H. And we could do this, you know, the way we did this over here. We could just, you know, load a 0 into the high part by doing clear, and then put a number into W and put that W value into FSR 0L. But those three instructions could be done with one, LFSR 0, 0x40. So whichever you prefer. So this loads the source address into file register 0, and then if we go load file select register 1, that loads the destination address into file select register 1. And now we have this pair of registers we could use. So we've got a number of things we could do. We could, you know, move FF indirect file 0 to indirect file 1. And indirect file 0 says, what's the value in FSR 040? Okay, I'm going to move from file register 40. INDF1 says, what's the value in file select register 1? Oh, it's an 80. Okay, I'm going to move to file register 80. So that moves from 40 to 80. And then you have to increment, right? And we could increment file select register 0L, increment file select register 1L. So now this is pointing to 41 and 81. And then if we do this move again, it'll copy from file register 41 to 81. And we need to do that 16 times, so we could do something like move LW. You know, there's 16 decimal, 10 hex. And so we could decrement file WReg and branch if not 0 to do more. We could put more right here. So that'll spin 16 times, taking 1 off of WReg each time. After WReg is 1, we've decremented it, branched, moved 1 more time. We'll decrement W register from 1 to 0. The not 0 will fail, and we'll be done with our looping. And then if you like, right, instead of doing this, you can do this in one instruction, which is just move FF postinc 0, postinc 1, as someone said in chat. And so this says read FSR 0L, FSR 0H, treat them as a 12-bit number. Whatever the number is, that 12-bit number, that's the number or the address of the file register I want to read from. And then do the same thing with FSR1. That gives me the file register that I want to move to. Go ahead and move from the from address to the to address. And then this postinc says after I've done that, increment FSR 0L and H and increment FSR 1L and H. Meaning increment it as a 12-bit number. So if FSR 0L was FF and we increment, it would increment to 0. And then FSR 0H would also increment. So it's a 12-bit addition instead of an 8-bit. And there's other ways you could do it. You could do it with the plus thing, right? So you could plus W0 plus W1, and since W is changing from 16 to 0, you could use that to move through the data that you're reading from and to, and so on. So you got options.
We could use move FF posting 0 and posting 1, right?
Yeah, that'll definitely work.
Okay. Oh, yeah.
Yeah, works really well actually. All right. Did anybody go back and try the floating point questions from the earlier homework? 128, 930.
I looked into it briefly,
Mm-hmm.
but I didn't. I kind of got confused a little bit.
Okay. Anything in particular that was confusing?
Just what bits or what when you try to break it into the 32-bit single precision.
Okay. So the book has a pretty good picture of this, right? So here's your 32-bit number. Actually, that's a general one. So here's a 32-bit number. This is the least significant bit over here on the right, bit 0. So your first 23 bits, the 23 bits on the right, those make up the fraction. And remember, it's not exactly the fraction because the fraction has a leading 1 to the left of the decimal point. That's not included in here. And then the next 8 bits represent the exponent, but it's a biased exponent. So it's not the actual exponent, it's the exponent plus 127. And then this leftmost bit, the most significant bit, that's your sign bit. And so if you wanted to write a formula to describe what your number is in terms of these three pieces, it would be negative 1 to the s. Well, that's just a trick. Because if s is 0, negative 1 to the 0 is 1. That's positive. If s is 1, negative 1 to the 1 is negative 1. So this negative 1 to the s is either plus 1 or minus 1, depending on what the sign bit is. And then you multiply that by your fraction plus 1, because there's that 1 to the left of the decimal point. And then you multiply that by 2 raised to the value that's stored in here minus 127. Because the value that's stored is actually your true exponent plus 127. So if you see a number like this, right, you take this sign bit that's a 0, so you're going to have a positive number. You take this number, which I believe is 126, and you subtract 127, you get negative 1. So you're going to multiply your fraction by 2 to the minus 1. And then your fraction is written as 0, 1 with a bunch of zeros. And to see what that corresponds to in decimal, right, put the decimal point right to the left of that and add a 1 in the beginning. All right, so what is 1.01? Well, this is the units place, 2 to the 0. This is the 1/2 place, 2 to the minus 1. This is the 1/4 place, 2 to the minus 2. So this in binary is equal to 1 plus 2 to the minus 2 is a quarter. This is 1.25. And so your whole number is 1.25 times 2 to the minus 1. So it's 1.25 divided by 2, 0.625.
I think it was the bias of 127 that was confusing me.
Yeah.
I couldn't figure out why it was negative 1.25 and 1.25 is translating to
Oh, okay.
the exponent there.
Got it. Yeah, so this is you know, the standard for this IEEE 754 was, decided by committee, and for whatever reason, the consensus seems to be that instead of using 2's complement or signed magnitude, they used what's called excess notation, where you just add something to the exponent. So the smallest you could have, if you had an exponent of minus 127, that would be all zeros. If you had an exponent of positive 128, that would be all ones. And then the double precision version, which is 64 bits, is exactly the same type of format, but different specifics. So we have 52 bits. So first of all, you have two 32-bit numbers. So you have one 32-bit number here and another 32-bit number here. And you put those together to pretend you have a 64-bit number. Alright, so out of those 64 bits, the 52 least significant bits, those are the fraction. Okay, so a lot more precision, more of those really, really small powers of 2 that give you, lots of things to the right of the decimal point. So 52 bits of fraction. The exponent gets a little bigger, so instead of 8 bits, we have 11 bits of exponent, so 8 times a higher exponent, and the bias is 1023. So again, your exponent goes from 0 to 2 to the 11th, 2048. And you subtract 1023 to find out what the actual exponent is.
I have a more generalized computer science question here.
Cool.
So we talked about this a little bit in our introduction to C class, Mr. Scott. Are integers still signed magnitude versus floating points and doubles that would be IEEE 754?
So integers in C, an int is usually a signed integer. So it's, depending on your architecture, it's either 16 or 32 bits. And it's just, powers of 2, 2 to the 0, 2 to the 1, 2 to the 2, up to, if it's 32 bits, 2 to the 31st. And when you take your number and look at it in binary, if that most significant bit, that bit on the left, if that's a 1, then this is a negative number. And you can toggle the bits and add 1 to find the positive value. And if this is a 0, then this is a positive value, and you can just add up the powers of 2 and see what the value is. And that's what a default integer is. Now there's also something called an unsigned integer, and it's stored exactly the same way. An unsigned 7 or a signed 7 are stored exactly the same way. But if we had an 8-bit system, right, and we wanted to store an integer, and we said integer I equals, 255, we would get an error, because that's too big to store in an 8-bit integer if we're using 2's complement notation. The biggest int is 127. But if I do an unsigned integer, this would just be stored as, 8 ones. And it doesn't so much affect how things are stored as how things are compared, right? If I compare this to, 127, well, if these are unsigned integers, I'm comparing this number to this number. Well, this number is a lot bigger. It's 128 bigger. So as unsigned integers, this would be bigger than that. But if I'm doing signed integers, this is -1. That's a lot smaller than 127. And so the way the compiler codes the logic to do whatever your C code is trying to do will be affected by the types of variables that you have, particularly signed versus unsigned ints. Now, if you have a variable that's a float or a double, it's all done with IEEE 754. And if you have the integer 1, it's stored as, a bunch of zeros with a 1 in the least significant bit. If you have a double that's equal to 1, it's not going to look anything like an integer 1. it's going to have some bits here and some bits here and some bits here. And it's going to have a really big exponent field because of that bias. Does that help?
Yeah, it does.
Okay.
We're gonna have a problem like this potentially on the test Thursday.
Potentially.
Okay.
So if I were to ask you a question, it would probably be, you know, take one of these things and write it as a floating point number, or take a floating point number and write it as one of these things. So conversion one way or another. And there's some examples in here. And there is a typo in here, I believe. So in this first example, 1100, that's the letter C. 1000, that is an H. And then 1010, so this part is actually an A, not a 9. So the conversion from binary to hex here has a typo. So if you're working through these, watch out for that. But let's do a practice conversion. So let's try. Let's write 0.1 in single precision floating point format using IEEE 754. So I'm going to (0.1) equals something times 2 to the something. It's a positive number, so we know what the sign bit's going to be. The sign bit's going to be a 0 because it's positive. And we want to write it as something times 2 to the something. And just like when you're learning scientific notation, there's a lot of ways that we can do this. So one way to do this is I could write it as 0.1 times 2 to the 0. 2 to the 0 is 1 times 0.1, that's 0.1. But that's not the normalized form that we want. So if I move this decimal point around, I can get my numbers in a different form. All right, so let's be careful. 0.1, I'm asking for, you know, converting this decimal number 0.1 to be something times 2 to the something. So first thing I want to do is convert 0.1 to binary. And I probably should have picked 0.3 because that already looks like binary. But the decimal number is 0.1. So how do we write that in binary? So do you remember the trick for converting numbers from decimal to binary? There's two ways. You can trial and error it. And 0.1 is not too bad, because if you get 2 to the negative 3, you're going to be close to what this is. But there's this trick we can use, right? So in 250, we learn a pair of tricks. If you have a number like, you know, 145 and you want to write that in binary, you keep dividing by 2. So 145 divided by 2 is 72 with 1 left over. 72 divided by 2 is 36 with nothing left over. 36 divided by 2 is 18 with nothing left over. 18 divided by 2 is 9 with no remainder. 9 divided by 2 is 4 with 1. 4 divided by 2 is 2 with nothing left over. 2 divided by 2 is 1 with nothing left over. And 1 divided by 2 is 0 with 1 left over. And then if I do 0 divided by 2, I'll just keep getting the same thing. And you know, this number is what's feeding the next row of this calculation. So you do this repeated division, until you end up with, 0, remainder 0. And this is your binary equivalent. So 1, 0, 0, 1, 3 zeros, and a 1. So 145 equals 1, 0, 0, 1, 0, 0, 0, 1. I wonder if that's correct. So 128 and 16, 144, 145. Hey, it worked. All right. So if we try to convert a number that's smaller than 1, like 0.1, we do the same kind of thing, but we multiply. So we say 0.1 times 2 equals 0.2. 0.2 times 2 equals 0.4. 0.4 times 2 equals 0.8. 0.8 times 2 equals 1.6. So we're multiplying instead of dividing. And the thing that we carry down to the next line is just the thing to the right of the decimal point. So on our next line, we're going to say 0.6 times 2 equals 1.2. And then we're going to do 0.2 times 2 equals 0.4. 0.4 times 2 is 0.8. 0.8 times 2 is 1.6, and so on. And then in this case, what we look at are these digits, these bits to the left of the decimal point. That's what gives us our binary equivalent. So if we copy those bits up, we have a 0, 0, 0, and then a 1, 1, 0, 0, 1, 1, and there's a pattern here. Right, and that'll just keep repeating. So this is what 0.1 looks like in binary. You can sanity check this, right? So this is 2 to the minus 1. That's a half, that's a quarter, that's an eighth. Well, an eighth is 0.125. That's too big. This is a 16th. That's 0.0625. That's smaller than this. So that seems like a good place for our first digit. So yeah, good question in chat. So somebody asked, is 0, 1 in decimal irrational in binary? So it's not irrational, but it is a repeating fraction, or a repeating decimal, right? So this 1100, 1100, that goes on forever and ever and ever. And so in school we would write this like, 1100 with a bar on top, which means this keeps repeating.
Oh, I have a quick question.
Sure.
So how do you know when to stop multiplying by 2 when your result is like 0 or 1 or something like that? Or...
So there's two answers. The first answer is, once I got to 0.4, I remembered that I had already seen a 0.4 after that. And so I'm guaranteed, this pattern is going to repeat 0.8, 1.6, 1.2. I know the next thing I'm going to see is 0.4, 0.8. So once you get to a number that you've already seen, you can just stop there and that pattern will keep replicating. I usually go a few spots beyond that just to sort of like see the pattern more clearly. But that doesn't always happen. It's possible that, you'll get ones and zeros that have no apparent repeating pattern. But if I'm doing 32-bit representation with this standard, I need 23 bits of fraction. So I would go until I had 24 ones and zeros, and I would stop there. And that's usually what a computer does. Yeah.
So, is that just the nature let's say you had a decimal that is just a regular rational number like 0.1 in regular decimal versus, I don't know, hexadecimal.
Mm-hmm.
Would numbers that look like a terminating rational decimal look like that in every number system, or is that just the result of what we're doing here?
It's an interesting question, and I don't think there's a easy answer that I can pull out of my head right now. There probably is a pretty straightforward answer. But for example, in decimal, the fraction 1/3 can't be written exactly. It's a repeating decimal, 0.33333333, right? In base 3, it would just be 0.1. That would be 3 to the minus 1. So some numbers that, don't come out nice and clean in decimal come out nice and clean in other bases. 0.25, takes 2 digits to write in decimal, takes 2 digits to write in binary, 0.01. So there's a mixed bag.
I never considered that. That's really weird.
You know what else is worth considering? So if we have a computer and we use floating point representation, we can't store 0.1 exactly. Right? And we also cannot store 0.01 exactly. It's another one of these repeating binary representations. Well, what if you're using a computer to do banking? Right? So a lot of transactions are, down to the penny. So somebody, puts a deposit into their account. It's usually, some dollars and some number of cents. So it's 2 decimal points, right? Well, if their paycheck ends with a 0.1, right, so they got paid, $90.10, and it ends with a 0.1, and you store this fraction in your computer, it's not exactly 0.1. It's always going to be a little more or a little less. And it's not a huge amount, right? It's way down in the 2 to the minus 23rd range. But it's non-zero. There's an error. And if you're doing banking where you're dealing with, billions of dollars or, millions of transactions where you keep adding up these things with these little tiny errors in them, those errors become significant, right? So you got the Office Space ATM rounding error thing. And that's a problem. That's a serious consideration. And so a lot of languages that are used in banking, like COBOL, for example, does not use floating point representation like this. They would use something like binary coded decimal, where they would actually store each of the digits in the decimal representation in a 4-bit quantity. It's a little harder to build hardware that manipulates that, but you don't have these rounding issues with decimal numbers. So there's all kinds of pros and cons to any of these representations. Yeah, there was a movie. I think there were multiple movies. But Office Space, which was a comedy, awesome comedy, by the way, they did that with an ATM system. But they messed up the decimal point, and so they made, like hundreds of thousands of dollars in the first day, which was a problem. But anyway, yeah, so that's a real thing. And I think someone did try an exploit like this once. All right, so that's one thing to know, is that like some numbers that are written nicely in decimal don't come out, as a precise representation in binary, and vice versa.
Kind of explains why you would see things like that even in decimal. They can be represented as just rational numbers in other numbering systems, but that had never occurred to me until
Right.
just now.
Cool. Well, when calculators first came out, right, you could type 1 divided by 3 equals, and then times 3, and then subtract 1, and you wouldn't get 0. You'd get some number that was like close to 0, but not exact. And it was because, early calculators didn't store 1/3 very precisely because it's got, rounding error on the end. And you can deal with that by putting in a few extra bits and keeping those so that you round things in the correct direction and so on. And when you convert a number into binary, right, you usually go out to the 24th bit. And if it's a 0, then you round the 23rd bit down. If it's a 1, you round the 23rd bit up. So just like we do in decimal, if it's a number below 5, we round down. 5 or above, we round up. All right, so we know what point 1 is in binary. Let's go ahead and convert it to floating point. So let me repeat this up here. All right, so there's our binary representation. And so now we want to put this in the form of something times 2 to the something. And so writing it in binary, I could write it like that. Something times 2 to the 0, but that's not normalized. So my goal is to get a 1 to the left of the decimal point. So I need to move the decimal point over 1 spot. And here's a question that none of us ever know for sure. If I move the decimal point to the right 1 spot, do I increase or decrease the exponent? You got a 50-50 chance.
You go to the right 4 places.
Mm-hmm. What do I do to the exponent?
You would multiply it by -4.
Yeah, so you subtract down. So if I move the decimal point 1 spot, this is 2 to the -1. If I move it a second spot, that's 2 to the -2. If I move it a third spot, that's 2 to the -3. If I move it once more, that's 2 to the -4. Or, you just start here and you go 1, 2, 3, 4, and then subtract 4. But that's what you're doing. All right, so now we've got a normalized fraction, right? We've got a binary number over here to the right of the decimal point. We've got a single 1 to the left. And now we're all set to write this thing in a floating point notation. So our fraction is going to be this thing to the right of the decimal point. And it's going to be all of that out to 23 bits. This is our exponent. And so it's -4, but we need to add a bias. So we add our bias of 127. So our exponent is 123, and our sign bit is going to be a 0 because our number is positive. And then you just sort of put all of this into the bin, into the bins that you find up here. So sign bit is 0. Exponent is 8 bits, and it's the number 123. So that's 64, 32, 16, 8, 4, 2, 1, I believe. That should be 123. And then we do our fraction, 100, 1100, 1100, and so on. And then if you want to write that in hex, you break it into chunks of 4 bits. And so this is hex 3, D, C, 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 C. And at the end here, it's going to end with 1100, and that last one is going to say round this up. So this last bit's going to be 110D.
I think your screen window's covering it up a little bit.
That last one's going to, thank you. That last one's going to end with a 1 after it, so that 0 is going to round up to a 1. So that last one will be a D. If I asked you this, I wouldn't ding you for that, but that's detail, right? So yeah, so 0.1 would be 3D, CC, CC, CD. All right, and then I mentioned there's special formats, and this is described in the text also. So one problem with, or one feature of this representation is we can't write a 0 like this. There's no way to write a 0 as, 1 plus a fraction times 2 to an exponent, right? Because if we have 1 plus our fraction, this is always going to be at least 1. And if we multiply by a power of 2, it's never going to be equal to 0. Right? Because 2 to anything is always non-zero, and 1 plus a fraction is always non-zero. So we have a special representation for 0, which is where the exponent and fraction are both 0. And if you have zeros in here for the exponent, and zeros in here for the fraction, well, this makes your real fraction as small as possible. It's just the number 1. And your exponent would be 0 minus 127. It's 1 times 2 to the minus 127th. It's the smallest number you could possibly represent in this format. That's the value that's used for 0. So exponent 0, fraction 0. And then if the exponent is 0 and the fraction is non-zero, that's a special way to represent a very small number. These are just the plain old representations we've been talking about. If your fraction is 0 and your exponent is 255, that's not exactly the largest number you can have, but it's close to the largest number you could have. It's actually half of it. But that's a representation for infinity, and it can be plus or minus based on the sign bit. And then if you use that same large exponent but a non-zero fraction, that's a representation for a nan, not a number. So you can use that to say this is not a valid number, and you can carry that around in calculations and so on. We get to play with some of this in 223. All right, so I had a question about arithmetic. So discussion, speculate how you would write an algorithm to multiply two floating point numbers. What about addition? So suppose that you had two numbers represented in this format where you've got a sign bit, an exponent, and a fraction. And let's say you've got two of these, so sign 1, exponent 1, fraction 1. You've got another sign 2, exponent 2, fraction 2. So this is n1 and this is n2. And you want to multiply them. So what would you have to do? What would your algorithm have to do from a very high level view? How would you multiply two of these floating point numbers to get a floating point number for their product? Any thoughts?
I'm not exactly how you do it in sign magnitude, let alone in IEEE 754.
Well, suppose you know how to multiply integers and how to add integers. You've already got something that will do that, let's say. How do you do this in scientific notation? So suppose we have two numbers. So let me call it m1 times 10 to the exponent 1 and mantissa 2 times 10 to the exponent 2. How do you multiply two of these things? We're going mathy today. All right, 5 times 10 to the 2 multiplied by 3 times 10 to the 4th. What do I get? I'm assuming this is covered somewhere.
Don't you get 500 and 3,000?
500, yeah, this is 30,000. So if I want to multiply them, what do I get? Without having to deal with lots of zeros.
Wouldn't it be 15 followed by 6 zeros?
There you go.
Okay.
15 times 10 to the 6th. I multiply the mantissas, right? And I multiply the exponent parts, right? Because, I mean, this is this multiplied by that, and I'm multiplying by this multiplied by that. I can multiply in whatever order I want. So I can take 5 times 3 and get 15. And here, what I wanted to do was take 10 squared times 10 to the 4th. But there's this thing called the law of exponents, which says this is 10 to the 2 plus 4, which is 10 to the 6th. So a general rule for this would be I would get m1 times m2, and that would be raised to 10. That would be multiplied by 10 to the exponent 1 plus exponent 2. And so if we have a way to multiply integers, well, you know, take your fractions, multiply them together. Take your exponents, add them. That's kind of, you know, nominally what you're going to get. So this will be like exponent 1 plus exponent 2. This will be fraction 1 times fraction 2. What about the sign bit? So suppose this first number is negative, the second number is positive. How does my answer change? Negative 5 times 3 is...
Negative 15.
Yeah, it just makes the product negative. And what if both of these are negative?
Positive.
Yeah, you get a positive. So we could make a little table.
So this translates exactly to accurately 754. Just multiply the fractions, add the exponents, right?
Well, almost, yeah. We'll talk about the almost in a sec. But yeah, basically multiply the fractions, add the exponents. And then for the sign bit, if this is the sign bit of your first number and your second number, what's the sign bit of the product? Well, this means S1 is positive, S2 is positive. Positive times positive is positive, so your product has a sign bit of 0. Here we've got a positive times a negative. That's a negative, so our sign bit is a 1. Here we've got a negative times a positive. That's going to be negative, so the sign bit will be 1. And here we've got a negative multiplied by another negative. That'll give you a positive, so the sign bit is a 1. So how do I represent the sign bit of the product in terms of the sign bits of our two numbers? What's the expression here? We're throwing back to 250. That's an XOR. So this could be, you know, S1 XORed with S2. All right, that part works exactly. The trick with, doing 5 times 3 times 10 squared times 10 to the fourth, 15 times 10 to the sixth. Well, what's the problem with writing this in scientific notation? What happens if you turn that in on your physics homework?
It'd be wrong because you don't have a decimal in the middle of your number.
Yeah, it's not normalized. So this really should have been 1.5 times 10 to the seventh. So this is the spirit of what we want, but we'd have to do some more work. We need to take this product that we got and make sure this fraction is normalized. So we might have to move that fraction's decimal point left or right to make sure there's exactly 1 to the left of it, and as we move that, we adjust our exponent. And also remember, if this is IEEE 754, this is not the exponent of our number. This is the exponent plus 127. So what goes in here is really exponent 1 minus 127. That's the power of 2 for the first number. And what we add to that is the exponent from the second number, minus 127. That's the power of 2 for the second number. This is the actual exponent we want. And to store it in floating point notation, we have to add that bias back. So these cancel, and it's really this minus 127. So there's lots of detail, right? But, somebody somewhere had to write code to do this. And probably the first times it was done, it was written in assembly language. But it's an algorithm. You spec out the steps, and you just kind of go through it, and you can do this. And there's odd cases, if one of these numbers is equal to 0, you got to do something special. Because you need your result to be 0, and that's got a specific representation, and so on. And then that homework question asked, what about addition? And I'm not going to spend time talking about addition, but if you have two floating point numbers and you add them, it's a lot harder than multiplying. Because this is, well, let me do x1 plus x2. So this is fraction 1 times 2 to the exponent 1 plus fraction 2 times 2 to the exponent 2. Well, have you ever tried adding numbers in scientific notation? It's actually harder than multiplying. So 5 times 10 to the 2 plus 3 times 10 to the 4. Can I add those directly?
I don't think you can, because you wouldn't, in algebra, you wouldn't combine like terms of different exponents, right?
Yeah. We don't have a rule for a times b plus c times d. We do have a rule for a times b times c times d. We know that we can multiply in any order, so we can multiply those and multiply those. But for addition, we don't have a rule like that. And this is actually asking me to take 500 and 30,000 and add them together. And I should get, 30,500, which is 3.05 times 10 to the 4th. So you have to normalize one of your numbers to make the exponent the same. Right? What I actually have to do is take 5 times 10 squared and write that as 0.05 times 10 to the 4th. Well, now I've got a rule. I've got this times 10 to the 4th plus that times 10 to the 4th. It's just this plus that times 10 to the 4th, 3.05. So when you want to add floating point numbers, you have to do this normalization step first, where you adjust one of your numbers so that both numbers have the same exponent. And the choice of which number you move takes an algorithm. And then you add your fractions and you preserve the exponent. And when you're done, you may have to normalize again, because this might be, too big, or these numbers might cancel each other in a lot of decimal places. So you have to do a denormalizing in the beginning, you do your addition, and then you do a renormalizing at the end, and you look for special values. And it's a lot of work. But, this is what computers do. All right.
Kind of a cheap hack to store and use bigger numbers, right?
Yeah, yeah. But if you need a wide range of numbers, possibly very large, possibly very precise, you got to do something. And most floating point systems use some form of exponent and mantissa for the representation. I mean, you have the option of just making, an integer that's 1024 bits long, but that's not very efficient and takes a lot of space and so on. All right. Shoot me an attendance ping. Send me a direct message. Let me know you're here. Let's take a 5-minute break, and then we'll talk a little bit about the final exam, and then we'll just kind of wrap up on some other stuff. So I'll be back in.
Can we ask some questions about lab 6 maybe?
Yeah, definitely.
Okay.
All right, I'll be back. welcome back. All right. Yeah. Let's talk about the lab first. So, lab 6 questions.
Even though it is due Thursday, I still kind of have a question. I ran into some weirdness on the last experiment
Mm-hmm.
where I was trying to implement the code to convert the characters from uppercase to lowercase and from lowercase to uppercase,
Okay.
while also ignoring the special characters.
Yeah.
And I tried a couple different approaches to this, but I noticed that sometimes the UR output would just skip letters.
Interesting. Particular letters or just randomly?
Kind of randomly.
Hmm.
What happened was I originally had it as its own separate function, and I noticed it would miss more characters, and once I decided to do a little test where I started adding no-ops to increase the number of cycles in the interrupt handler,
Okay.
and it would miss even more characters, so I was assuming that the more cycles I use, the less letters I'm getting in there. The way I eventually got it to the point where I could just have it will get it right the first time every time.
Okay.
It will either be like missing one little character every time it repeats, or it misses one little character every time, every other time.
Okay, so was this only in your code for experiment 3, or was this experiment 2 also?
Only for experiment 3.
Okay. So...
I only had 2 if statements basically managing what if it gets uppercase, lowercase, if it's a special character, ignore it. But it would get it right, like if I put the word the hello world message in there, it would get it completely right the first time, and then every other time, for some reason, it would skip the second L in hello and get the rest of it right.
Interesting.
And then I tried all lowercase test, and then 3 special characters like exclamation point, open curly brackets, characters we just want to leave alone. And it correctly left those alone, and it got it right the first time, and then it missed the S in test the
Interesting.
second time, and then it got it right again, and then it alternated back and forth.
Okay. Huh, that's intriguing. So we can definitely look at that in lab hours, but my first suggestion would be just comment out your if statements and your code that makes those adjustments. Leave everything else in the code exactly the same, but just take out the logic that tries to change the characters. And the goal here would be to try to get the smallest set of code possible that still has this misbehavior. And then that gives you a smaller space in which to search for what the actual bug is. And it's always possible, one with MPLab and a simulation, and also, since some of the stuff is interrupt related, it's always possible that there's something that's just going to be flaky, right? And we can try to systematically find what that bug is, and that may not work because it may be a bug that's going to move around. But my first suggestion would usually be try to start, commenting out sections of code, and see if you can find a simpler set of code that exhibits this behavior, and then dig around in that.
I did cut down how many if statements I was using to manage the code, and I started substituting them with skip statements to save even more code. And if I go ahead and I just comment out all of my code that ignores special characters, meaning if I do have an exclamation mark, it's going to add or subtract.
Right.
It's still going to try to convert it, even though it doesn't know it's a special character, but it gets it right every time.
Okay.
Do that. Or if I code that converts it to uppercase or lowercase, it will get it. It'll leave the special characters alone every time and get it right every time. But then I don't have the code that uppercase is to lowercase.
Okay.
Lowercase is to uppercase.
Well, that's a really good debugging job actually, because that kind of pins things down pretty nicely. Come by lab hours if you can, and we can definitely work through it. But I'm going to take a stab in the dark here, and suggest that somewhere you're doing a call without a return. Like you're doing a call, but maybe somewhere in an if statement, instead of coming out of the call, you're doing a go to somewhere else, and that eventually your stack is overflowing, and that's causing your processor to reset, and that would cause characters to get dropped probably. That's just kind of off the top of my head, something that could be going on, but like I say, if you can come by after class to Zoom hours, we can definitely play around with it in the simulator.
Sure.
It sounds like an intriguing bug. All right, cool. Any other questions or discussions about Lab 6? And so Lab 6 has to be turned in by Thursday, by the start of class. Even if you have slip days left, I need all the work turned in by the final exam. So, you know, take it as far as you can, and turn in what you have by the start of class Thursday. All right, well, let's talk about the final exam. To whatever degree we can. So final exam is on Thursday, August 26th. It will be available on Canvas at 12 p.m. and it will be due at 2 p.m. And it will be similar to the midterm. It will be on Canvas as a PDF file, and it will be a series of questions, and what you want to do is write up your answers to that in some kind of electronic format, and then save it as a PDF, upload that PDF to Canvas. It's a rigid deadline, 2 hours, unless you have a time extension. And it will open up exactly at 12. So if you normally come into class a few minutes late, you probably want to try to get here, you know, by 12, or, you know, download it by 12, so you can get the full 2 hours. Canvas will let you turn it in late, but, you know, 10 points a minute penalty for turning it late. So don't turn it in 5 minutes late to try to, you know, get that one last thing to work, because you'll lose 50 points. So turn it in by 2. And it'll be an upload, and it's got to be a PDF, same as usual. There's an honor statement in the beginning. Go ahead and read the honor statement, and then at the top of the document you're going to turn in, just write the words honor statement : and type your name next to it. That's your honor statement. Everything should be typed up, unless you decide to include flowcharts. I'm not going to require flowcharts, okay? People's flowcharts in labs have been fantastic. So I feel like that's, you know, done its purpose as far as giving you that tool to use at your discretion going forward. So if you want to include flowcharts, right, you'll need to find some way to scan them and include them in your PDF. But that's at your discretion. And it will be 6 or 7 questions, and mostly, you know, similar to homework questions. So So go through your homeworks, go through your labs, right? It will be questions about, you know, writing code to set up the I/O subsystem, deal with the tris register, add con1, using the port registers, being able to use bit mask so that if you input, 8 bits from a port, but you only care about these 2 bits in the middle, how do I look at just those 2 bits and ignore the other parts of those 8 bits that I read in? Well, you use a bit mask, right? So AND it with something to make those bits you don't care about zeros, and just look at those 2. Maybe do some rotates or a swap to move it into a different position if you want to do something like, add it to another number and so on. So the stuff you've done in labs with I/O, so that's fair game. Definitely an emphasis on the second half of the course, though. So second half has been primarily, doing calls and returns, specifically for interrupts, right? So understanding how interrupts work, the different sources for interrupts, how to configure those sources, how to set their, enable flag, if they have a priority option, their priority level, if they have, things specific to that subsystem, like, for the timers, you can set 8 bits or 16 bits and so on. So those details, maybe what edge and interrupt from the outside is going to interrupt on, rising edge or falling edge, and so on. And then, enabling interrupts at a global level, so global interrupt enable high and low, and knowing what to do when an interrupt occurs, which is, have some code at location 8 or 18 to handle the interrupt. You have to clear the interrupt flag when you're done processing it, and you have to return with a ret fee to re-enable interrupts as well as return. So all that stuff with interrupts, right? You're allowed to use the data sheet on your exam. I went ahead and pulled out a subset of the data sheet that was that quick data sheet quick guide that you've seen on Canvas, but I have another one where I just pulled out the registers of interest, and you can make yourself one of these. So intcon and all of the integer interrupt related registers, but then I also put in the timer registers. So timer 0, 1, and 2. I don't know if I did timer 3, and I think I put in the A to D registers in here. On the ECCP and so on. So you can make yourself composites of the data sheet. Data sheet's over 300 pages long, but you can make yourself a digest of the parts that you're interested in. One way to do that is just print your PDF, but for the output device, say print to a PDF, right, or save to a file in Microsoft or something. And you can usually specify page numbers. You can specify ranges or pages with commas, so that's how I make these guides for myself. So so definitely interrupts, all of those aspects of the interrupt subsystem. Definitely timers, right? Timer 0, 1, 2, and 3. And we've done tons of homeworks. You've done a few labs involving those. So being able to set up the timer registers, the configuration registers. Possibly having those timers cause interrupts and so on and so forth. And then the indirect file register stuff that we talked about last week and you just turned homework in on. Being able to, write a piece of code or analyze a piece of code or answer questions about doing indirect references. Those are the main new things that we've gone over. We talked a little bit about A to D conversion, so I could ask you some conceptual questions on that. I'm not going to have you write code for that because we haven't done that yet as a class. So possibly a question on scientific notation, but that's not going to be a big part of it if it's on there, and stuff like that. Let's see, what else have we done? Let me go through what we've been doing. So everybody can write code. Everybody knows how to code instructions in binary or look at a binary instruction and know what it does. Brush up on the destination bit and the access bit. Make sure you're comfortable with those, right? And how they relate to specifying a 12-bit register versus an 8. And being able to put a comma 0 or a comma W after an instruction to say put the result in the W register. Let's see.
If the A bit is 0, it's going to the general registers, right?
If the A bit is 0, it's possibly going to the special function registers.
Okay.
And it's kind of weird because it's called an access bit, but it's a 0 that actually makes it do the accessy kind of thing. So if you look in the quick guide, there's a picture here, figure 5.6, that has a nice little synopsis. When A equals 0, the access bank is used, which means you're either coming from general purpose RAM or special function registers. And it depends whether the number that you're specifying is below 80 or above 80. And then when A is 1, it's just business as usual. That the 8-bit number that you specify in the instruction, that's the file register you go after. So 0 is the special case. And then the destination bit right before table 20 figure 20-1, you've got a description. Destination bit 0 says put the result in W reg, 1 says put it back in the file reg. And that's probably all you need to know on those. Let's see, what else have we done? A lot of coding in this course, right? So we've spent a lot of time just digging into different ways to write things in assembly language, right? So that's all good stuff, and it's stuff you've practiced every lab and so on. Oh, stacks, push and pop. So if I ask you anything about that, it'll be kind of, the conceptual kind of questions like you saw in homework. Like, here's a call instruction, show me what the stack looks like afterwards if this is what it looked like before. So you call, you push something on the top of the stack, you change the stack pointer, and so on.
Is it going to be about the same number of questions?
I don't remember. I think it's 6 or 7 questions, probably. So yeah, maybe the same number of questions about as the midterm, but possibly slightly longer questions. I don't want it to take you the full 2 hours because I want you to have some breathing room in there. But you'll definitely want to work quickly, and you'll definitely want to try to start on time. I think that's pretty much the course. Yeah, the midterm was kind of longish. So as with the midterm, I recommend hopping into Zoom. I think there was one thing on the midterm that, didn't make sense. I think I asked for a destination bit on an instruction that doesn't have a destination bit. So, if you're in Zoom, I'll just announce things like that. And I'll leave you alone the rest of the time. But if you're not in Zoom, then you got to figure out how to do impossible questions and such. So hop into Zoom and hang out there while you're doing the test. All right, other questions, concerns about final? All right, well, let's talk a few minutes about memory and storage. So this is not on the exam, but this is technically part of the course. So like I said, there's 4 parts of the book, and I think most of these are a few pages long. But there's 4 parts of the book that we don't actually get to. So one is on performance, and that relates to the idea of like pipelines, which we've talked about a few times, right? This idea that while you're fetching one instruction, you can be executing the previous instruction, and while you're executing this instruction, you can be fetching the next instruction. And so we overlap these steps, and we don't increase the speed of a single instruction, but we increase the throughput, the number of instructions that complete in a certain amount of time. It's a really clever trick, right? If it takes you, 4 hours to paint a room, and you get, some friends to help you, can you paint the room quicker? Well, if you invite one friend over, I'll work on the left side, you work on the right side, there's a good chance you'll get the room done, quicker than 4 hours, possibly closer to 2 hours. And if I invite 3 friends over, so there's 4 of us, maybe we each do one wall, but now we got to have 4 sets of paintbrushes and 4 sets of rollers and 4 sets of masking tape and 4 paint trays, and the overhead starts to increase. And if I invited 40 friends to paint a room, would I be able to finish it in 6 minutes? Probably not. Because 40 people trying to paint one room doesn't work very well. You get in the way of each other. You don't have 40 paintbrushes, so you have to borrow them, or maybe you have 40 paintbrushes but only 20 rollers. And if 2 people are ready to use a roller at the same time, right? So you get into resource contention. And so there's number of processors, and then there's like performance. And there's some point where having more resources improves your performance, but at some point it drops off. And so this is stuff that you would talk about in a computer architecture class related to parallelism and scalability and stuff like that. But in a CPU, right, you can find ways sometimes to break instructions into, say, 10 steps and have, 10 instructions executing simultaneously in a way that they don't step on each other. But think about our little PIC processor with a 2-stage pipeline. So we've got fetch and execute. And fetch and execute. And fetch and execute. So we fetch the first instruction. There's nothing else we can do because we haven't fetched, an instruction before. We fetch the first instruction, we execute it. So it takes, 2 clock ticks to finish that instruction. But while we're doing that execute, we're fetching the next instruction, and we execute that in clock tick 3. And at the same time, we fetch the third instruction, and we execute that in clock tick 4. So 4 clock ticks, we've done 3 instructions, right? Kind of looks like 1 instruction per clock tick, even though each instruction takes 2 ticks. But think about this fetch execute business. Suppose what I'm doing here is, increment file register 20, and over here is increment file register 40, and here is, add W to file register 21. When this instruction is executing, what's it doing? It's incrementing file register 40. So it has to read file register 40, add 1 to it, write it back in. And while it's doing that, it reads something from location 40, it increments it, it writes it back. At the same moment, the CPU is doing what? Fetching another instruction from memory. And if you had a single memory, this execute would be trying to write a new value of, file register 40 at the same time that the CPU is trying to read the next instruction of your program. And you would have memory contention. Because most memories, you can write, you can read, but you can't do both at the same time. And so trying to, write this location while I'm also trying to read, the instruction at location 6, right? I'd have a memory problem. So this is why on the PIC processor and on most RISC processors, you have two memories. You have a data memory and you have a program memory. Because you're fetching from the program memory, your execution involves modifying the data memory. If they're physically separate memories, they don't fight with each other. So the reason we have a separate program memory from a data memory on the PIC is so that we can have this pipelining. And all of that is just a nod or a motivation to the general idea that when you design a computer, you don't just get to say, I want to do this and this and this and this and this, right? It's not like making a bouquet of flowers where you just pick all your favorites and you put them together, right? If I want to have a single memory to keep the cost of my system down, I can't do a pipeline like this. Unless I make my memory what's called dual ported, so I can read and write two different locations at the same time, and now it's more expensive and more complex and takes more power. And if I want a longer pipeline to make my CPU run like it's faster, I'm going to need more resources, because I might have 5 instructions in the process of executing. Maybe both of them need to use an adder. Well, I might need more than one adder in my CPU now. I might have one adder that's being used to calculate addresses, another adder that's being used to calculate branch locations, and the third adder that's being used to do addition. So my architecture teacher years ago, he called this the n-way teeter-totter problem. So like a teeter-totter or a seesaw, right? You sit on one side, the other side goes up. If you sit on that other side, then this side goes up, right? Well, imagine that with, like several planks of wood, and whatever you do to one plank, right, all the other planks change in response to that. That's what computer architecture is all about. You don't get to just kind of like pick your favorite characteristics. So if you could do that, what would your favorite characteristics be? Suppose you were trying to design the microcomputer chip that was going to, take over cell phones and laptops and everything else, right? What would you put in your dream computer chip, your dream CPU, to make it, the chip that everybody and anybody has to have? Everybody wants this chip. This is gonna make you a billionaire. So what would your characteristics be of your dream CPU?
Hybrid architecture, ARM, RISC-V, and x86.
Okay, so so we'd want some of the benefits of a reduced instruction set and the benefits of a complex instruction set, and I'll throw in compatibility. Since you named specific processors, right? We'd like it to be compatible with code that's already out there. If I come up with a new instruction set, I can't take my .exe files from Windows and run them without recompiling them. So we'd like compatibility. What else? Everybody gets to pick one of their favorite features. All right, I'll toss one out. Let's say low power, because I want this to be able to be used in a cell phone. I don't want a giant battery pack, so I want this thing to be very low power requirements. Can anyone think of any other features that would be nice?
Easy to manufacture, so it's in stock or available.
Easy to manufacture. Manufacturing prices are through the roof, and the cost of a new foundry is doubling every few years, and it's well beyond the billions of dollars mark at this point to make a new chip foundry. So yeah, we'd like something easy to manufacture. What else? Or what do you want in a laptop? Dream laptop. Nobody's a gamer out there?
I am.
What do you like in your dream laptop?
It'd be super cool to have replaceable components.
Okay. What else?
Great graphics capabilities.
Okay. I'm just going to say, from the perspective of a CPU chip, on-chip gizmos. So it would be nice to have a chip that I mean, on-chip processors are kind of a lame usually, but you know, it would be nice if you got your CPU chip and it had like a really nice NVIDIA or some other GPU built in. You got any concern about CPU speed?
I'm concerned about thermals, but I guess that falls into your low power category as well.
Not necessarily. I would list that separately. So you definitely want a fast chip, right? Everybody wants a fast chip. It's the number one thing you see when you go to buy a computer. How many gigahertz is it? It's a meaningless number, but it's a marketing thing, right? We probably want low temperature. Kind of goes along with low power, but maybe not. Could just be a really good cooling system, you know. So you want low temperature. How about reliability? Do you want a cheaper laptop that breaks every 2 days? Probably not. But while we're at it, right, we'd probably want something that's low cost. If you can have all of this for, you know, $3,000 or all of this for $300, you probably want the $300 one.
Lots of BCIe lanes.
I don't know what a BCIe lane is.
I said PCI.
Oh, yeah. Okay, good. And lots of RAM, someone said in chat. We'd like connectivity, whether it's PCI or something else, right? Our PIC chip has 20 pins, and what did we discover? Those pins get used for multiple things. So if you want to do A to D conversion, or you want to read a binary number, you got to go through all this code to set up things in registers to say, well, this is an input, and this is an output, and this is an analog, and this is going to do an interrupt, and so on, right? It'd be nice if it had, you know, just a million pins on it, so that each pin had its own purpose, right? So you know, you can go on and on. You can make your kind of dream list, and these things all fight each other, right? If you're going to be low cost, you're not going to have a ton of stuff on board. You're not going to have a fancy GPU with lots of cores on board or lots of RAM. It's not going to be really fast, right? It's probably going to be a little power hungry because the low power technologies are more expensive to manufacture. If you try to make something that's super low power, right, it's probably not going to be as fast as something that takes more power, right? Speed costs heat, right? We know this. And RISC and CISC are kind of fundamentally in tension with each other, right? If you want a lot of capability in your instruction set, it's going to be a complex instruction set, which means it's going to be harder to manufacture. It's going to be larger. And, you know, small size is nice. Not every processor goes in a cell phone, but it's nice if you have the option, right? But if you have a physically small chip, it's probably not as sophisticated as, you know, a large, you know, 1-inch square die. And so these all kind of fight against each other. And so it's you know, part of a much larger discussion how you kind of dial in the particular requirements for your processor. And it depends, you know, who your customer is. If you're building a chip that's going to go inside a key fob for your car so you can open it and lock it remotely, right? It doesn't need to be super fast. It's doing, you know, one piece of code basically. That's a pretty simple function. Wait for a button press, and then depending on the button, send a signal out, right? but you got to do some kind of radio transmission, so you might want a chip that has a radio transmitter inside. And there's, you know, a line of PIC chips that have RF transmitters built onto the chip, specifically for using them inside, you know, things like remote control unlocks and stuff. But you're probably not too worried about speed. You're probably very worried about reliability, because if somebody drops their key and now they can't unlock their car or turn off their alarm, that's a problem. You're probably really, really worried about power, because you don't want to have to like change your battery every 6 weeks in your key fob, right? But it's a commodity item, right? It costs you, you know, $100 or so to get a replacement key. You just pass that cost on to the customer. So we're probably not too worried about low cost, right? Because we're going to charge an arm and a leg for these things. And everybody's got to have a key to their car. So this is all like, you know, other aspects of engineering and stuff like that. But it's you know, like I say, part of this bigger conversation that, you know, the software and the hardware and the economics and the physics and everything else, those all come together. And, you know, at one time you kind of like designed a computer and you built it and you sold it and people wrote software for it and people used it and everything was kind of like, you know, separate. And that's really not the case anymore. And so whether you're, you know, an electrical engineer or a computer scientist, or you're doing computer engineering or game design or medical systems or, you know, whatever, you don't really get to have blinders on and just look at one piece of the puzzle anymore. You're kind of necessarily, at least peripherally, involved with lots of different aspects of this. All right, well, that had nothing to do with memory and storage. I was really talking about performance. I'm going to call it good there. We got 10 minutes left. I'm not going to try to squeeze a large lecture into the last few minutes. So I will leave it there. If you didn't send me a attendance ping at the break, send me a ping to let me know you're here. But I don't need another ping from everybody, because everybody's here that's here. So all right, well, I'll leave it at that. I'll let you out 10 minutes early. I will start the video upload and switch over to my Zoom lab hours, and come in if you want to work on the lab or ask questions and so on. Yeah, 10 minutes, go crazy. And otherwise, thank you for the summer. I definitely enjoyed it. This has been a really fantastic class as far as the people in it, and I've really appreciated your hard work in here. So I will see you on Thursday. Hopefully everybody will rock the final exam, and we'll be good for a few weeks. Unless you're at WSU, in which case you're already in school. So, all right. Have a good one then, and I'll see you in office, or I'll see you Thursday.
Are you starting up Office immediately?
I need a few minutes to start an upload of the video and stuff, but I'll be heading over there in the next few minutes.
Alright, I'll catch you there in a second.
Okay, cool. All right, have a good one. Bye, everybody.
Thank you.